Welcome all of you. Since last class, we started discussing about two-dimensional NMR. In last week, I introduced to you about what is 2D NMR, why do you require 2D NMR, and I said clearly, if we have a pulse sequence designed with n time periods, out of which n minus 1 are incremented and 1 is constant, and we have n time periods, you do n dimensional Fourier transformation, you are going to get n dimensional spectrum, frequency spectrum. So, we can have 1D, 2D, 3D, 4D, etc. And I also explained to you about the limitations of these experiments, time constraints, and the size of the molecule, both we discussed. And of course, for 1D and 2D NMR, maybe few minutes you can get these days, 25 to 30 minutes, or for 3D maybe few days, 4D few weeks it goes. And like that, it becomes very lengthy as the experiment becomes longer as you go to higher and higher dimensions. And also depends upon the molecular size. I also explained to you how, depending upon the molecular size and type of information you want to derive, you can even decide what is the type of experiment you want. Whether you want 2D, 3D, accordingly you can plan it. And I also explained that 2D can be classified broadly into two divisions. One is correlated experiment, other is resolved experiment. Both could be homonuclear and heteronuclear. And I explained a lot of examples I gave. For example, about cohomonuclear experiment like COSY, TOCSY, etc. Heteronuclear experiment like HSQC, HCAR, HMBC, etc. Varieties of experiments are there. And any 2D experiment, I also explained to you how do you interpret the 2D data if you have a particular peak either on the diagonal or a cross peak. So, depending upon how the spins evolve in the T1 and T2 dimension, and how the magnetization is getting transferred from one spin to another spin with which it is interacting, we will have the peaks in the T1 dimension and T2 dimension accordingly. So, this is what we discussed, and we also saw simple examples of spectra of 1D, 2D, 3D, etc. varieties of spectra, how the appearance of spectra are there. So, with the basic introduction to 2D NMR, in general multidimensional NMR, from now onwards we will start going to specific experiments. Today I am going to discuss about what is called two-dimensional correlated spectroscopy, also called 2D-COSY, correlated spectroscopy. COSY means correlated spectroscopy. And the requirement for this type of experiment is the nuclear spin should be scalar coupled. There must be an interaction between the nuclear spin, J coupling must be there. So, let us see what is this 2D experiment, how it works, we can start discussing. Of course, COSY experiment, as I said, is a very simple two-pulse sequence. As I told you, for any two-dimensional experiment, you have a preparation period, evolution period, mixing period, and a detection period. And preparation period is the one where the nuclear spins are allowed to prepare, attain thermal equilibrium. Then you apply a radio frequency pulse, 90-degree pulse. During this period, the nuclear spins evolve under chemical shift of J coupling, under different chemical shifts of spins. And afterwards, you apply 90-degree pulse, that is a detection pulse, start collecting the FID at a constant time period, fixed time. And both these pulses are 90-degree pulses. Of course, you can apply X or Y depending upon your choice. And this is a detection period, evolution period, and this is a preparation period. Of course, it is a very simple two-pulse experiment. You may ask me what is mixing time here. There is no mixing time. This itself you can consider as a mixing time. Mixing time is absent here, mixing period. So, in general there are 4 periods. Here I told you already, mixing period is optional. We do not need to have a mixing period. We do not have it here. In principle, some people will explain that second pulse itself as a mixing period. Does not matter. So, this is the two-dimensional experiment, simple pulse sequence. Remember, COSY is a simple two-pulse experiment. Sorry. What COSY gives? Connectivity among immediate coupled partners. Of course, it can also give Lagrange interactions, but immediate coupled partner we can immediately see that. For example, if I have a molecule like this, a chain, there is a chain is broken somewhere here, assuming that there is no interaction between this CH2 and this CH2. Then if I do a COSY experiment, COSY tells me this is correlated to this, we will get a correlated peak that tells me this CH group is sitting next to CH2. And I get a correlation from this to this, telling this is sitting next to this, and also it gives correlation to this, saying that this is sitting next to these two. Similarly, this gives correlation to this and this, telling it is sitting between these two. This is sitting here, it correlates to this alone, saying that this is isolated. Similarly, we can get the correlation between this and this. Very easy. And interpretation of the 2D-COSY spectrum is pretty simple. Please remember, COSY gives you connectivity pattern among immediate coupled partners. Let us see how the COSY pulse sequence works. This is something about conceptual understanding that is needed. We will start with a 2D-COSY for a uncoupled single spin, a one proton which is not coupled to anything else. Simple example is CaCl3 molecule. We are looking at the proton. We will not worry about the natural abundance carbon 1% abundance. Assume that is not coupled to proton. So we are having a single proton, one spin, uncoupled to other thing. Of course, it won't couple to chlorine. That's what I want to assume. So and we will start with the 2D-COSY spectrum of a single spin. Let us see how this thing works. This is a usual pulse sequence which I already told you. First, we are going to apply a 90-degree pulse. What does it do? We have been discussing. 90-degree pulse tilts the magnetization to xy plane. Depending upon whether you are applying pulse along this axis or this axis, it will tilt it to other direction because the three are orthogonal to each other. That's what we have been discussing. So first 90-degree pulse tilts the magnetization to xy plane. What will happen afterwards? The magnetization starts evolving during this time. This is a free precision time, during which it evolves according to its chemical shift. Because there is no coupling here, it is single spin. So it has to evolve according to its chemical shift. All right. After a time period t, this proton would have moved to some distance. The vector has moved to some distance. That we have already been discussing. It goes by pi into nu into t1. T1 is the time you allow for the spins to precess in the xy plane. And how much it has moved is given by this expression. All right. And now once you start moving like this, for example, somewhere here, you can resolve this into the two components along this and the x-axis and y-axis. And we have a cosine component here and a sine component along x-axis. The magnetization can be resolved into two components, this vector. Cosine component is along y and sine component is along x-axis. All right. What does second pulse do? This is what the thing, what is happening to the vector during the period t1 after applying 90 pulse. The second pi by 2 pulse acts only in the y component. That is what is happening. And the x component is not at all affected. And it continues to precess the way it is precessing. It is not affected. Only y component of this is getting affected. Then what happens? We will allow it to wait for some time and collect the signal. Do the Fourier transformation of this. It produces a spectrum with a single resonance line, because a single peak. Because one proton is there, no other thing is a CaCl3 molecule I have taken, only one proton and it gives you one chemical shift, one peak. What is the intensity of this? It depends upon how far it has rotated, how far it has precessed. Because we will take the component of this along the detection axis, y-axis, cosine component we will consider. And let us consider one of the peak. We will measure the intensity of this peak, which varies as a function of cos theta. I told you cosine of this time period, it keeps on varying. Given by this expression, the amplitude of the signal as a function of t1, how it varies is given by this expression. What we will do is take that peak and start measuring the intensity of this as a function of t1. I keep on varying the t1. Initially the signal is, let us say, negative, intensity comes down, becomes 0, goes positive, and after some time it keeps coming down like this. So it starts like this, okay, and then becomes 0 and then goes up like this. It starts oscillating. It becomes a oscillatory function. Essentially what we did by doing this variation of the varying t1, we could build a pseudo FID. That is what I said about in general introduction when we were discussing about 2D NMR. We can build a pseudo FID in the F1 dimension. All right. At longer times, what will happen? Signal intensity completely diminishes. Why? Because it is also relaxing. It is oscillated, at the same time decaying exponentially. It decays. And decay is also there because of relaxation. So as longer values of T1, you keep on waiting for a long time, signal intensity becomes 0. That is what we saw in the FID. Keep collecting. After a long time, there won't be any signal at all. Maximum signal is during this period, keeps decreasing with time. So after a long time, there won't be any signal, completely diminished. Now we will do the Fourier transformation in the T2 domain. What you will get? We get a frequency data because we are collecting a signal at a fixed time period, that is called a F2 period at a T2 period, and I collect it, and there is also data in the other time domain also. I collect the data in the frequency in the F2 domain, which comes from the F2 or the T2 period, and also time domain data in the other T1 period. So both are there. What I am going to do is I will do the Fourier transformation of the FID in the T1 domain. I can do separately, individually Fourier transformation in both the domains. If I do the FID collected during T1, if I do the Fourier transformation, I get the frequency F1. This gives the frequency to me in 2 dimensions now. When I do the Fourier transformation in the F2 dimension, I get omega 2. When I do the Fourier transformation in the T1 dimension, I get omega 1. Now, a Fourier transformation in both the dimensions gives me spectrum in 2 dimensions, omega 1, omega 2. Both the dimension I get the frequency spectrum. True. I am collecting the FID both in T1 period and T2 period. I am doing the Fourier transformation in both T1 and T2 period. I will get a frequency spectrum like this. Where does the peak come? The double Fourier transformation of this gives a peak where the 2 signals intercept like this. It comes exactly in the diagonal, because this signal, whatever was its frequency in the T1 period, continues to remain same in the T2 period also, because it is a single spin. There is no way it can interact with any other spin. So it has not given its magnetization to any other thing. There is no transfer of magnetization. It was during the T1 period, it has some frequency omega A. It remains same in the T2 dimension also. They getting unaffected. As a consequence, we get a peak on the diagonal, because if from this peak sitting at the top, come vertically you get one frequency, go horizontally you get another frequency. This omega A frequency is identical in both the dimensions. That is why it is coming on the diagonal. This is what happens. So if I get take a molecule, only single spin is there, single proton, not coupled to anything else, and do a COSY, you get only one peak on the diagonal. That is what you should understand. Let us take the example of 2 peaks. Instead of 1, we will take the example of 2 peaks, that is A and X. And now I am putting a condition to uncoupled spins. What do you mean by uncoupled? JAX is 0. Coupling is 0. I assume there is no coupling, but there is a chemical shift of A, chemical shift of X, both they are different. The chemical offset frequencies are different. Let us see what happens to this type of molecule, to uncoupled spins in the COSY pulse sequence. When I do the Fourier transformation of these 2 uncoupled spins, exactly if I take the frequency A, okay, it remains same in this axis and also in this axis. Take the peak here, go horizontally, I get a peak, go vertically, you get a peak, and this frequency is same. So this, if I say this is nu A correspond to frequency A, or chemical shift correspond to A, this also chemical shift correspond to A. It is a diagonal. Now come to this peak. Again from the peak, sitting on the peak, go horizontally you get a peak, go vertically up you get a peak, and this is frequency X. That means this is also X, this is also X. That means when I have a diagonal peak, its frequency remains same both in the T1 period and in the T2 period. Its frequency is identical whether you do it measure in the F1 dimension or in the F2 dimension. That is what the peak which is coming on the diagonal in a two uncoupled spectrum, COSY spectrum. We have 2 peaks coming on the diagonal, and draw a line vertically, go to along omega 2 axis or along omega 1 axis, you get the identical frequency for both of them, and this is what it is. And if I can take a projection of this spectrum, we get 2 peaks like this. I can take the projection along F1 also, then also I get 2 peaks. That means whatever you take a one-dimensional spectrum of these 2 uncoupled spins, 2 molecules, let us say water and CaCl3, which are not coupled at all, they are 2 different molecules. Take the NMR spectrum of it. proton NMR spectrum, you get 2 peaks, one for CaCl3, one for H2O. So that will be on the diagonal. So plot, take the projection along this axis, you get 2 peaks, one for CaCl3, one for H2O. Here also same peak CaCl3 for this. If you take it horizontally, if you draw a line, this is also CaCl3 peak and this is a water peak. If you assume this is CaCl3 and this is water, this is also water peak, this is also water peak, this is also CaCl3, this is also CaCl3. That means if I take the projection, I can take it along F1 axis or F2 axis, does not matter. When I have two uncoupled spins, we get two spectrum. On either dimension, we get the spectrum, which is nothing but a simple one-dimensional spectrum. Okay? And what do you understand from this? For uncoupled spins, the peaks always come on the diagonal. And if you take the projection of these uncoupled spins if are there and the projection along F1 or F2, it corresponds to simple one-dimensional spectrum where you get single peaks. And now let us see what happens in a realistic example. I take 3 solvents, Ca3CN, H2O and CaCl3, all the 3. I take the COSY spectrum of none of them are interacting, they are all 3 different molecules. CaCl3 comes here, H2O comes here, Ca3CN comes here. One is at close to 2 ppm, 4.8, 7.2 ppm, I get 3 peaks. So 3 peaks will be there on the diagonal. So you take any peak on the diagonal, go vertically up, go horizontally, you hit a peak. And that corresponds to peak which is Ca3CN coming at 1.94 ppm. Go to the next one, go vertically, go horizontally, you hit the same peak on both the dimensions that correspond to water peak coming at 4.8 ppm. Identically, you can talk about CHCl3 also. That is how it is. So if you take the spectrum of 3 solvents which are non-interacting, then you get 3 peaks on the diagonal. That is what the spectrum. So you simply understand the logic. If I take the 2-dimensional COSY spectrum of uncoupled spins, they always appear on the diagonal. So they take the projection of that frequency in F1 axis or F2 axis, it remains same, it pertains to simple peak corresponding to what you get in the one-dimensional spectrum. Alright. With this we will go further. We will try to understand the COSY spectrum of 2 coupled spins. What happens in the same example, earlier AX was I set 0, but now I make it non-zero. Let us see what happens if it is non-zero. Exactly, A and S are coupled with a coupling constant A, and I have the chemical shift nu A and nu X. Fine. We will understand what is happening with the pulse sequence. First, 90-degree pulse makes the magnetization associated with spin A. I will talk about only one spin right now for new spin A. What happens to spin X? It should be identical because the interactions in NMR are mutual. We will understand what is happening to spin A. 90-degree pulse makes the magnetization associated with spin A to precess during T1 at its chemical shift nu A, because it has a chemical shift nu A. This is the free precession period. After application of pulse, you are not doing anything. Spins are free to precess. Also, it has coupling, that one thing. But what will happen when it is precessing at this frequency? And this frequency, it produces a frequency peak at this frequency which is same in both the dimensions. Nu A, I am considering only nu A, like assume if it is uncoupled, there is only one chemical shift, it gives a peak which is nu A comma nu A, what we observed in the previous slide. Uncoupled spin, frequency remains same in both omega 1 and omega 2 dimensions. So it gives a peak. What do you call this peak? This is a diagonal peak, that is what we observed. So nu A, because it is precessing at its own frequency in both the dimensions, both T1 and T2 period, it gives a diagonal peak which correspond to identical frequency in both T1 and T2 periods. Further what happens? The second 90-degree pulse transfers part of this magnetization to the coupled X spin. During the process here, spins are interacting. It will transfer part of its magnetization to coupled X spin. That is a polarization transfer, what is called magnetization transfer that takes place. And what will happen to this transferred magnetization? It gives it to which spin? It gives to X spin. A spin gives part of its magnetization to X spin. Why? Because they are J coupled. There is a scalar coupling between these two. So it will transfer part of its magnetization to X spin. Then what will happen to that? This X spin not only precesses at its own frequency, also it precesses at the frequency of A. So it will now X spin will precess both at frequency of A and also at the frequency of X. That is what happens. So then it will give me a peak corresponding to two different chemical shifts in two dimensions. That means it gives nu A comma nu X. That means I get a peak. We remember we understood how to interpret the 2D spectrum. We get a peak in where if you get the peak, go along omega 1 dimension, you get a frequency corresponding to chemical shift of A. Go along the other dimension, you get the chemical shift of X. Both will be there. You will get the peak which correspond to two different chemical shift in two dimensions. All right. What do you call this? This is called a cross peak. When the chemical shifts are identical, nu A comma nu A, it is diagonal. But nu A, the spin A also gives a cross peak in addition to diagonal at frequency nu A comma nu X, which correspond to cross peak. Okay. What is that? For example, if it is like this, it gives a peak here, nu A, and also gives a peak here. Let us say this is A and this is X. So nu A gives a peak at its own frequency and diagonal and also gives a frequency at X. Understand? It gives two different chemical shifts in two different dimensions. And this peak is called a cross peak. But one sitting on the diagonal is a diagonal peak, I told you already, this is a cross peak. So nu A gives a cross peak at the frequency nu A comma nu X. Meaning, go to along the chemical shift of A, go horizontally, you get a peak here, come vertically down, you get a peak here. This corresponds to chemical shift of X, this corresponds to chemical shift of A. That is what it means. So you get a peak, cross peak, where in one dimension you get the chemical shift frequency of one, in other dimension you get the chemical shift frequency of the other, called cross peak. So the precision of magnetization during T1 and T2 period for spin A, it means is not identical. They are no longer at the same frequency. See, for the spin A, in the T1 period it is at frequency A, in the T2 period it has frequency nu A comma nu X. So we have two frequencies for this peak. One comes on the diagonal, which comes at the identical frequency of its own in both the dimensions, and also you get a cross peak which comes at the frequency of its own and also a peak at the corresponding frequency of the X spin. Here frequency I mean is the chemical shift. That means you get a diagonal peak which corresponds to chemical shift of A in both the dimensions and also get a cross peak which corresponds to chemical shift in one dimension of A in one dimension pertains to chemical shift of X in the other dimension. This is how you are going to get peaks for the A. Okay. Then I will ask a question. What is going to happen for X spin? We are discussing about A spin. Please remember, I was telling you, interactions in NM are always mutual. If A is interacting with X and giving its magnetization to X, same thing happens. X also give to A. That means X spin behave identically. It evolves at its own frequency in T1 dimension and also at its own frequency in the T2 dimension. That means it gives a peak at nu X comma nu X, which is a diagonal peak, and also nu X in the one dimension, in the T1 dimension it gives a peak at its own chemical shift, whereas in the T2 dimension it gives a frequency at a chemical shift of A. You understand? Very interesting thing. A gave a peak at its own frequency and a frequency of X. Similarly, X will give chemical peak at its own frequency and also at the frequency of A. What does it mean? It means A will give rise to diagonal peak at its own frequency, X will give diagonal peak at its own frequency. A will give a cross peak with X. X will give with a cross peak with X. X will give cross peak with A. So this is what it is. So we have diagonal cross peaks pertaining to both these planes. And this is the pattern we get in the COSY now. What is that pattern? We will see. The diagonal peaks will have 4 peaks in the square pattern. Why it comes? If I take this one, diagonal peak for, let us say this is the chemical shift of A, it will have 4 peaks in the square pattern. Why 4 peaks? Because A is split into a doublet because of X. Similarly, X will have 4 peaks in the square pattern. Diagonal peaks have fine structure of 4 peaks, and this separation corresponds to AAX, JAX. This also corresponds to JAX. Identically for this also. So the cross peaks also will have the fine structure similar to this. Now A will give its own frequency as diagonal. It also gives cross peak at the frequency of X. These are also 4 peaks. This is cross peak. What does this will give? Again, this separation will give you J coupling. You understand? Now what happens for X? X also gives a cross peak with A. Not only at its own frequency, gives cross peak. So we will get 4 peaks for cross peaks similar to square pattern here. So basically what is that you are going to get is you will get for diagonal for each of them 4 peaks, cross peaks, 4 peaks. So totally you are going to get 16 peaks. For both spins 1 and 2, the diagonal peaks are in phase doublets. Okay, we get 4 peaks, that's fine. But further I am going to tell you the diagonal peaks are in phase doublets in both F1 and F2 dimensions. Center the frequency nu1 and nu2, and that separation is J. What do you mean by in phase doublet? That we have to understand. If I have a doublet like this, A is coupled to X, A is a doublet. Similarly, X is a doublet. On both the frequencies like this are in phase. They are all, let us say both are positive like this. This separation gives you a coupling constant JAX, and this is called in phase doublet. They are in phase. So both the dimensions, I have 4 peaks diagonal peaks are in phase, and if I take the projection, both are in phase. If I take this projection, both are in phase, both are positive. So both the dimensions, they are in phase doublets. It means. What about the cross peaks? Cross peak always arises in COSY because of transfer of antiphase coherence to antiphase coherence. What is an antiphase coherence? We were discussing this during spin log time discussion, and the spin echoes, and also inept. We discussed a lot. J modulation at the various places. We discussed this antiphase. The antiphase is like the cross peaks are antiphase, that is, one is positive, other is negative like this. You can get this is called antiphase doublet. And the cross peaks are always antiphase in both the dimensions. For example, this is the 4 cross peaks for the 4 peaks square pattern for cross peak. If one is positive, other is negative. In this dimension, again here this is positive, and then you go, this is negative here. So in this dimension it is positive and negative, here positive and negative. This is how it goes. What it means? The cross peaks are antiphase doublets in both the dimensions, both in T1 dimension and T2 dimension, or omega 1, omega 2 dimensions. Similarly, diagonal both have in phase doublets in omega 1 dimension and omega 2 dimensions. So this is the pattern. So and doublets are always out of phase by 90 degree. That is what is called antiphase here. So in homonuclear 2D COSY, always the cross peak appear as pairs. Homonuclear, it is always a pair, and it is symmetric with respect to diagonal. Obviously, logically it is true. When I have a peak like this, a homonuclear case, chemical shift in this ray, in this both are identical, because same nuclei we are considering both the dimension, and this is the diagonal. If this peak comes here, and this is the diagonal peak, and if a cross peak comes here, cross peak comes here, because interaction is mutual. So with respect to diagonal, they are always symmetric. Cross peaks are always symmetric with respect to diagonal, and they appear as pairs. This is the important property of 2D-COSY. Homonuclear. Remember, it is homonuclear. Heteronuclear, it won't be like this. That is different. So, COSY pattern of two coupled spins, how do they look? Is like this. If I have two weakly coupled spin system, I already discussed this in a Popper nomenclature, A and X spin. What is the pattern you are going to get? You get doublet for A and doublet for X. So, if this is the chemical shift of A, this is the chemical shift of X. Similarly, this is A and X in the same order. This is diagonal. This is F1 dimension. This is always F2 dimension. I get 4 peaks here. Exactly like this. 4 peaks. A appears at its own frequency. They are called autocorrelation peaks. A will correlate within itself because there are two doublets. This will correlate to this. This will correlate. This will give cross peak to this. This will give cross peak to this. So, as a consequence, you get cross peak. This and this gives cross peak between themselves. They are called autocorrelated peaks. And similarly, X also gives 4 live peaks in the square pattern. That means this is also autocorrelated peak. This and this are correlating, give rise to cross peak between themselves. X appears. Now, both A and X spins give autocorrelated peaks. Finally, what is going to happen is A frequency will give rise to cross peak at its coupled partner X. Okay, this like this. X, this is X also gets modulated because of frequency A. It gives its energy or magnetization to A. X will give to A will give to X. They will give rise to cross peaks like this. As I told you, they are in phase doublet, all are positive. Here antiphase doublet. In this dimension, if this is positive, this is negative. In this dimension, if this is negative, this is positive. That is what it means. So, this is the COSY pattern you are going to get in two spins which are coupled, weakly coupled. So, signs and signs of diagonal and cross peaks are like this. Both are, if I say closed circle, positive, open circle, negative. That means here negative, positive, positive, negative, positive, 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 positive. Both the dimension positive. Here one dimension positive, negative, other dimension also positive and negative, 2 peaks. So, they are antiphase character like this, plus plus, minus minus like that. So, if you want to plot the spectrum, this will be like this. Both are in phase in both the dimensions. Here one is positive, other negative. Both are antiphase or cross peak in both the dimension. In this dimension also antiphase. In this dimension also antiphase. So, diagonal and cross peak structure can be understood like this. If it is a diagonal peak, it is like this. If it is a cross peak, it is like this. If I take the projection of one of the 4 peaks, if I take the projection, this is the cross peak pattern, projection both the dimensions. This is the cross projection of the diagonal peak in both the dimensions. So, please remember, COSY diagonal peaks are in phase in both dimensions, cross peaks are antiphase in both the dimensions, and this corresponds to positive peak, this corresponds to negative peak. Okay, with the now since the time is getting up, we will continue with the further discussion on the COSY in the next class. But so far what I discussed, I explained to you, COSY is a simple two pulse sequence, 90 degree T1, 90 degree T2, that is all, 2 pulse sequence. Preparation period is there, evolution period is there, and detection period is there. Mixing period is absent. What is going to happen? I took the example of how the spins evolve. After 90 degree pulse, magnetization comes to x axis, xy plane. It starts processing. It will have x component, y component. Okay, x component is one thing which keeps processing, it does not get altered. Y component is the one which you are going to detect. It will have projection along x axis and y axis, cosine and sine component. The cosine component is the one what we are anyway going to detect it, and depending upon how much it has processed, intensity changes. I took the example of one weakly one spin which is not coupled at all, isolated spin. I told you it comes on the diagonal whose frequency remains same in both the dimensions. Took an example of two spins uncoupled. It gives 2 diagonal peaks. Frequency remains same in both the dimensions for that. Then I took the example of coupled spin. Then I said coupled spin, we get diagonal peak, 4 peaks of square pattern for both the A and X spin. Cross peaks also give 4 peaks in the square pattern, but I said diagonal peaks are in phase in both the dimensions, all are positive signal. whereas the cross peaks are antiphase in both the dimensions. One is positive, other is negative in both the dimensions. And this is what we understood, the structure of cross peaks and diagonal peaks in a two simple weakly coupled spin system. And we will continue further about how we can use COSY in understanding further. In the next class we will discuss this. Thank you.